Okay, so we looked at basic thermal concepts including heat and internal energy and temperature last time. Now we're going to look at the processes of heat transfer. Most of this will probably be revision of something that you probably learnt in your science lessons in previous years, but it's still worth having a go at and having a look through. Okay, so we're going to look at conduction, we're going to go look at convection, we're going to look at why some materials are better conductors than others. We're going to look at reducing convection, insulation, by trapping air. We're going to look at radiation and how that's different to conduction and convection. We're going to remember and look that black is a great radiator, silver is a poor radiator. And we're going to look at different examples of heat transfer and again how we could improve or increase heat transfer and how we could reduce or shut off, or as best we can, heat transfer. To remind you, objects have energy just by nature of existing. They have potential energy. The potential energy they have is determined, well, the chemical energy of the actual substance, but also any forces between them if it's a solid or a liquid, and the kinetic energy in various forms, and that kinetic energy is related to the temperature of the object. The greater the temperature of the object, the greater the kinetic energy, and vice versa. The more kinetic energy the particles have, the greater the temperature. And temperature itself is a measurement of average kinetic energy. So, heat transfer. When a hot body is in contact with a cold body, heat will be transferred. What does that mean? Last time I said that heat is a process. Heat is the energy that is transferred. Where does that energy come from? It comes from the internal energy of one body. Where does it go to? It goes to the internal energy of another body. So, hot things lose internal energy. That energy in joules is transferred to cold things that are in contact with it, and their internal energy increases. As the hot thing loses internal energy, its temperature decreases. As the cold thing gains internal energy, its temperature increases, until the temperatures match. At the moment those temperatures match, those two objects and any other objects who have the same temperature are in thermal equilibrium. Thermal equilibrium means that the object is not having an overall transfer of energy with the surroundings. Now, that doesn't mean that it's not giving off heat. It is. Every object in the universe gives off heat. How much heat it gives off depends on its temperature, but every object gives off heat. However, when I say there's no overall transfer, that's because it's also receiving heat from the surrounding objects. And as long as the amount it gives off is equal to the amount that it receives, the total energy will stay the same, the total internal energy will stay the same, and the temperatures will be the same. So heat is transferred. So energy is transferred from the fast-moving particles on the left to the slower-moving particles on the right, meaning that the fast-moving particles will slow down and the slow-moving particles will speed up, which is, as I said earlier, the same thing as temperature. Momentum is conserved. Energy is conserved. Total energy is conserved. And heat always flows from hot to cold. In fact, this is such an important idea, but it's got a name, which is the zeroth law of thermodynamics. There are actually three other, two or three, so important and fundamental that we call it the zeroth law. So that's the basics of heat transfer. Heat always flows from hot to cold. But how does it do it? Well, the three main methods of heat transfer you hopefully remember from earlier classes are conduction, convection, and radiation. Conduction is the transfer of heat by collisions. It's best happening in solids. In solids, the particles can vibrate, but they can't actually independently move. They're not like gases. Okay, so the objects wibble and wobble, as I've tried to show here, and as they do so, they bang into and pull and stretch the objects, the particles near them, but are not wobbling so much, which makes them wobble more, and these wobble less, which means that the heat gets transferred along. And if this is continuously being heated, if this end of our rod is in a fire or is on the outside where it's hot, then eventually that heat will be distributed into the interior. Imagine a brick put in a refrigerator. After a while, it's all cold. If you take it out, then it's going to start warm up. But which end warms up first? Which part of the brick will warm up first? The outside. And by conduction, that heat will transfer to the inside. After a while, the entire brick will be at the same temperature, thermal equilibrium, as the outside. All solids transfer heat by conduction. Metals are better at it. They're faster, they're quicker, they are much better at conducting heat. They're better at conducting heat for the same reason they're better at conducting electricity. They have electrons that are free. Metals bond, metallic bonding, leaves over free electrons. Free means they're not attached in any particular shell or orbital to any particular atom. Like atoms of a gas, they're free to move around the object. That means that if you heat them, they get lots of energy and they're free to go and quickly pass that energy on through collisions to the rest of the object. So metals are better conductors, quicker conductors, because of these collisions. Convection is our second method of energy transfer. And in convection works with fluids, i.e. gases and liquids. In the example here, which is a sort of pan or a pot of a fluid, the bottom is heated, the fluid near the bottom therefore gets hot by conduction. It conducts through the surface. Because it's hot, the particles spread out. Because the particles are spread out, it becomes less dense, and because it is less dense, it therefore rises. Now, obviously it can't leave behind nothing, so the colder fluid on either side goes to be warmed. As it goes, it gets warm, which means it rises. As it rises, it cools down, which means it sinks. This tends to lead to what's called a convection current or a convection pattern, which is a very characteristic pattern and feature of convection. It occurs in all sorts of environments, not just heating water, which we can see here, but even on global scales. For example, convection currents carry heat away from the Earth's core. Convection currents drive our atmosphere. Convection currents drive our oceans. So convection currents are very, 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 very important in many aspects of physics. The final method of heat transfer is radiation. Heat is transferred by direct electromagnetic radiation, in other words, by a form of light. Now, light, as we think of it, is just electromagnetic radiation that we can see, that our eyes can detect. But there is an entire spectrum out there. Black is very good at emitting radiation and white is very bad at emitting radiation, and shiny is the worst of all. The actual radiation that's given off depends on the temperature. Here's a human. We're 310 Kelvin on average. So we give off radiation in this part of the spectrum. And this part of the spectrum is called the infrared. Things that are hotter than us, for example, different types of stars, they give off radiation, they give a lot more radiation, and they give off radiation in a much greater band of wavelengths, including the visible light. The sun has its peak right in the middle of the visible. This is not a coincidence. Okay? We have evolved to make use of the sun's light. Our eyes have evolved to make use of it. So every object, as I said earlier, gives off radiation. Every object gives off heat. But most of it we can't see. You can see it, however, with an infrared camera. And this is an infrared camera. It's a picture taken of a racing car. There's the driver's head. Here's the back of the car. You can't quite see the front. And you'll notice inside, you can't see through things with infrared. You can sort of see through things like smoke a bit better. But you can't see through solid objects. But the engine gets very hot. And that heat is conducted to the outside of the car in that area. And that's what you can see. The tyres through friction with the ground become very, very, very hot. So you can see that the tyres, the edges of the tyres here that are in contact with the ground get very hot. You can even see where the tyre has just been on the road gets very hot because it conducts that heat to the road. So this is an infrared image. The colours, of course, are false. They're generated by a computer. They just show it's giving off a lot of infrared here, a bit here, and very little where it's black. So conduction, convection and radiation. Just to remind you, here are two Porsche cars. Which one would you like to have on a hot day if you want to stay cool? Well, you want the white one because it's the worst absorber. On a cold day, which one would you want to have to stay warm? Well, you'd still like the white one because white is the worst emitter and the worst absorber. If you want to be in thermal equilibrium with your surroundings, better take the black car. But you'll be hot on a hot day and you'll be cold on a cold day because black is good at absorbing heat on a hot day, but it's also good at getting rid of it on a cold day. If you want to stop heat transfer, that's insulation. Here's a diagram of a house which shows different forms of heat transfer and places that the heat is transferred. How can we stop some of that heat transfer? Well, for example, windows, double glazing. Instead of having a single pane of glass, you have two panes of glass. Why? Because it has to conduct, then it has to convect, then it has to conduct again. A cavity wall works in the same way. Instead of having one wall, you have two walls. However, you can make a cavity wall insulation even better by putting foam inside. By putting foam inside, it has to conduct, then it has to convect, then it has to conduct, then it has to convect, then it has to conduct, then it has to convect, etc., etc., etc. Further question, how can we keep liquids hot or cold? Well, the perfect device of doing that is known as the Dewar or vacuum flask, a thermos flask. A thermos flask has at its core the liquid, hot or cold, whatever you want to keep it. That is kept in a glass bottle with two walls and a vacuum beside. Vacuums, you cannot have conduction through a vacuum. You cannot have convection for a vacuum because both of these need particles. The only thing you can get through a vacuum is radiation. So it cuts down on the energy transfer. It's got silvered surfaces because that's worst at radiating. So it cuts down on the radiation. Of course, this big glass thing has to be kept inside the container. But again, you want to minimize the contact between that container and the actual glass walls. So you just have these springs to keep it in the middle, a rubber, and of course a bung on the top to stop anything escaping. And that way you keep your hot liquid hot or your cold liquid cold. I think we've completed most of the objectives. Using heat transfer methods, we can transfer energy between objects. This affects the internal energy of an object, but what other properties can heat transfer change? That's what we'll look at next time.